All right, so we're going to learn the mean value theorem for integrals. We looked at the mean value theorem for derivatives, which talked about the average rate of change. So when you think of integrals, you're thinking of area. So the mean value theorem for integrals talks about where the area for this rectangle would equal the area that's under the curve. So what that means, if this area under the curve here, maybe this is time, and maybe this is velocity, which would be measured in some kind of distance per time. And we looked at the area under the curve then. If I accumulate that, what I'm actually accumulating is, if I multiply time times some kind of distance per time, when I multiply, those two things cancel out, and I'm left with a distance. So the integral for this would accumulate the distance that you traveled maybe over time. So the difference is we're going to figure out what that accumulation is. And we're going to find that average value where that occurs. So what would happen is I could draw underneath the curve, I could draw some kind of rectangle that's going to have the area of this rectangle would equal the area that's under the curve. So where are those two things equal? So in this case, where is sort of the pink part equal to the gray part there? And that's what the average value is. Now they use the notation, let's see, so they'll say, let's see, average value. They'll use the symbol F of C for average value. So F of C is going to be the height of this rectangle. And then the C value is that X value. Where the height occurs. So this C value, if I come up to that curve, where that C value occurs, it's the Y value that corresponds with that. So that's what the average value and the C value are that they're talking about. So if you look at the area of this green rectangle here, the area of the rectangle would be base times height, so the length of this side would be B minus A, times the height of the rectangle here, which is F of C. And then that would equal the area under the curve. The area under the curve, we said, was the sort of pink color. And to find the area under a curve, we can integrate. We would integrate this from my lower bound to my upper bound, from A to B. And that curve we called F of X, whatever it happens to be. So that's where those two things are equal. And here's that mean value theorem then, or they'll call it the mean value rectangle, is that grayed out part there. All right, so let's look at a sketchpad simulation. This is a pretty neat simulation here that shows you a mean value theorem for integrals. So if you look at this, we have the area under this curve here, and what we want to do is we want to figure out, we want to create the rectangle so that the pink area is equivalent to the green area. So the area of the pink rectangle equals the area of the underneath the green curve there. So we got to estimate. So if you're looking at this, and this is more fun to do this all together here. So if you look at this, I'm guessing maybe just a smidge lower, maybe like right there. So I'm going to guess that value right there. So we're going to see how well I did here. All right, they're going to draw the rectangle so that it fits perfectly. That's pretty darn good. You should be impressed. If you were here, you would give me a round of applause for that one. All right, let's try another one here. So that area was above the curve. Here's another one. The area is the, not above the curve, above the x-axis there. So if I drag this up here, now my pink rectangle's outside there a little bit. So I want the pink area to equal the blue area. So if we were doing this all together, you would be shouting, higher, lower. There we go. Let's try that and see how we did. Oh, okay, not as good as last time. So the area of the pink rectangle would equal the area of the green, greenish area under the curve. All right, now if you look at this one's a little bit different because now some of the areas above the x-axis, and in terms of integrals, we think of that as being a positive value. This area over here that's below the x-axis, we would think of that as a negative. So this one we have to kind of think about, you know, this part is a negative value, maybe like, I don't know, this little bit of it, you could think of as being, let me do it on the board here. Say maybe this part and maybe like that part kind of cancel out, and then we got to try to figure out where would that rectangle have to go then to balance out the rest of this green area here. So let's see how we can do with that one. It looks like there's more green area above the x-axis than below the x-axis, so I'm going to say this pink rectangle has to be above the x-axis. I have a feeling I won't be so good on this one. So I'm trying to, you know, sort of look at this pink region and this pink region here, and I want those to have the same area as, you know, what I have left out here that's not shaded. I'm going to try there. I don't know how well I did on this one. I set the bar too high on the first problem there. All right, so I did not do too well on that one. All right, let me clear this. And then let's try one more here. All right, so now if you look at this one, you have area above and below, but we actually have more area that's below the x-axis than above the x-axis. We have more negative area than we have positive area. So I would be asking you in class, which direction do you think we have to go for the rectangle? And hopefully you would all be shouting out, you have to have the rectangle be below the x-axis to make that area equivalent. So somewhere down here. Now if I'm looking at this, I'm looking at this region here and this region here look to be about the same. So they kind of add up to a 0. So it's really this positive area and this negative area that we have to balance out. So I'm going to try dragging this down a little bit more here. I'm going to say about there. I don't have a good feeling about this one. Wasn't even close. So that's kind of the idea. The average value rectangle can be above the x-axis or below the x-axis. It's going to depend on you know, what your curve looks like. If there's more area above the x-axis, it'll go above, and if there's more area below, it'll go below. So let's figure out how we can do this with some calculus. So mean value for the integrals, that's this formula that we came up with right here. This was the area of all right, so this is the area of the rectangle, and then this is the area under the curve. Okay, we wanted those two things to be equal. So the average value, if I solve this equation for f of c, if I get this by itself, this 1 over, this b minus a is going to divide on both sides there, and it's just going to end up as 1 over b minus a if I divide this. You could write it this way too, but it's usually written as a fraction out in front there, right? Divided by b minus a. It's the same thing, but this is going to be the notation that you will see most often. Okay, so we're going to use that equation then to come up with the area under the average value, that f of c. What's the height for the rectangle going to be? So if you look at the first example there, find the average value of the function. We've got f of x equals x squared minus 5x minus 1, and we're looking just from 0 to 2. So let's go through and use our formula. So we want average value, that's the f of c. So that equals 1 over b minus a times the integral from a to b, f of x dx. So A and B are the endpoints for my integral, so 2 minus 0. I'm integrating from 0 to 2, and then my function was x squared minus 5x minus 1. So if I integrate that thing there, I have a 1/2 out in front. If I integrate x squared, I get x cubed over 3. If I integrate 5x, I get x squared over 2, and I still have that 5 out in front. If I integrate -1, I get -1x. And I'm going to evaluate that from 0 to 2. I should put the other side here. This equals f of c. So if I plug in my upper bound of 2, I get 8/3. Minus, if I plug in 2, that'd be 4, 20 over 2, which would be 10. Minus 2, and if I plug in that lower bound, it gives me 0. So inside here, I have negative, let's see, 12, 36, so 8 minus 36 is going to give me negative 28/6. I'm sorry, thirds. And then if I multiply by that half, I get negative 14/3. And that's my f of c value there. So that's the f of c. That would be the height for the rectangle. So if you think about this curve in terms of the problems that we've done, this is a parabola that opens upward. We're looking at the graph from 0 to 2. Whatever it happens to look like, I don't know where it is here. Suppose it looks like that, and we're looking at this area in here. The y value we came up with was a negative value, which means when I draw that rectangle is going to have a height of negative 14/3, which means the rectangle is going to end up below the x-axis. Okay? And that kind of makes sense. If you look at the graph, the area will be below the x-axis. So the second part then, sometimes, and this is not asked as often as the average value, because the average value there's lots of application problems for. Sometimes they'll ask, what's the x-coordinate, the c value that's guaranteed by the mean value theorem for integrals? So what is the x value that corresponds with that y value of negative 14/3? So my f of c, negative 14/3, that's my y coordinate. The c value is just asking for the x coordinate that goes with that y coordinate. So you just set your function equal to that f of c value we just came up with. So x squared minus 5x minus 1 equals that value we just came up with, which was negative 14/3. You're going to solve this equation. If you don't like the 3, you can multiply everything by 3. 15x minus 3 is negative 14. I can put the 14 on the other side. If I add 14, I'll get plus 11. And then, of course, this doesn't factor, so then we have to do quadratic formula here. So if I plug in, let's see, opposite of b plus or minus square root of b squared, 4ac, all over 2 times a, which is 6. This is going to give me 15. That simplifies to the square root of 93. Okay, so either one of these values, here's a decimal if you prefer a decimal, 0.893. Both of those x values would give you that y coordinate. It kind of makes sense he came up with 2 values because it's a parabola. You have symmetry over the axis, so really this would go back some. So whether I use this x value for that height or this x value for that height, it would give me that same rectangle there. Right, so that's what you do with those homework problems.